Hello and welcome to this final video from section 2 about telescopes and imaging. This is a video on telescope location, and this is a fairly short video. Hopefully we can go through it pretty quickly. Okay, so when we want to look up into the stars and out into space, we like to use a telescope. Why do we like to use a telescope? Because it can magnify stuff and we can see dim things. We can get lots of detail, so through this magnification we get high detail, high resolution, and what else can you think of? We can see all the EM spectrum, so see parts of light that you can't see with the normal eye, the naked eye. Spectrum. I think that's a good amount of reasons there. So these are all considerations we're going to take when we make a telescope. These are all things we're making a telescope for, but there's no point placing our telescope somewhere on Earth where we're not going to be able to do all of these things. Now, what do we see above these telescopes here? These are radio telescopes all looking up into space, and what is up above them? The sky. And the sky is a barrier between the telescopes placed on Earth and the stuff out there in space. We have the sky, which really is the atmosphere, and if light is travelling from outside of the atmosphere up in space down through the atmosphere and then to these telescopes, that can have an effect. The reason that we see stars twinkling with our naked eyes is because this light that's coming down from stars has to pass through our atmosphere, and our atmosphere is made up of lots of particles of gas which are floating around. We've got currents of warm air moving around, and that can have an effect on the path that light takes as it moves through. It can disturb it, and so looking at a star, it doesn't appear steady because we're seeing well, what scientists they call it atmospheric seeing. So the twinkling effect is there because light gets bashed around by our atmosphere. The atmosphere can have the problem where it causes some refraction, because we're going from one medium, space, into another medium, air. So it can cause refraction. Some light can be absorbed. Here is some more information about some of the problems caused by our atmosphere. Up here on the side here it says percentage of radiation reaching the ground. So here we're looking at frequencies all along the electromagnetic spectrum, and so here we've got radio waves. They're mostly getting through UHV, ultra high frequency, and VHF, very high frequency radio waves. So these are basically shorter radio waves. They're getting through. The smaller frequency microwaves are getting through, but then look, we've started getting areas here where there's not much light getting through, and look right down here, percentage of radiation reaching the ground. There's a whole section of the electromagnetic spectrum here that does not reach the ground. If we're trying to study light or EM radiation given out by stars in this range, between a frequency of 10 to the 11 Hertz up to 10 to the 13 Hertz, we cannot see these from the ground. Also, look here, any frequency greater than 10 to the 15 cannot be seen. So from Earth, percentage of radiation reaching the ground, X-rays are not reaching the ground. 0% of X-rays from space reach the ground. 0% of this high frequency UV reaches the ground. There's a bit of UV reaching the ground here, and this is the stuff that gives us sunburn. All the visible reaches the ground. That's good. That's what we're seeing at night. But look, there are basically huge chunks that cannot be seen from the ground because they are absorbed by the atmosphere. So astronomers need to think very carefully about where they place their telescopes. And if you're going to build your telescope on Earth, you want to try to do it. So if we're talking about an Earth-based telescope, you want to do it somewhere where you can minimize the effects of the atmosphere. Minimize the effect of the atmosphere. So where do we do that? We do that in places that are very high up, because the higher you are, the less atmosphere you've got above you until you get up into space. We also do it with places that have got, hopefully, quite still air. So naturally, around the Earth, there are some places that are very turbulent and some places that are very, the atmosphere is more chilled out, basically. And we want to also do it with places where there is low light pollution. What do I mean by light pollution? Hopefully you could explain this. But look, here's an example. We've got two pictures of the United Kingdom showing light pollution. This is pictures of the Earth taken from space at night. This one on the left is from 1993 and the one on the right is from 2000. You can see that, so look up here in Northern Ireland, for example, it's definitely brighter here. London is bigger. We're becoming more electrified and there's much more light pollution, and this poses a problem for scientists, for astronomers, because you want to go to an area of low light pollution, because if you're somewhere with high light pollution, you're not going to be able to see the stars because the sky is going to be lit up by the street lights around you. That's why it's very difficult for us to see stars in Dagenham. That's why you're much better off going out into the countryside. So that areas up here in Scotland might be quite good because there's very little light around here. It's very rural. This whole region here would be quite good because there's not much light. But the weather conditions are also an issue. So the UK is not actually great for doing astronomy because we get so much rain coming in off the Atlantic. There are places in the world, however, that you'd want to go where they're high up, there's still air, there's low light pollution, and they get clear skies, so no problem with weather. So if you're going to do all this on Earth, that's what you need. You're also practically going to want a cheap location. You're not going to want to put it somewhere that's very, very expensive because you're going to want to spend more money on your actual instruments than where you're going to place it. But that's a practical concern that scientists have to face. Or, if we want to avoid the problem of the atmosphere altogether, we could do a space-based telescope. This is the Hubble telescope, and it's based in space. And as you can see from this picture, it is outside of the atmosphere. So down on Earth, you've got these clouds and you've got this atmosphere to contend with that disrupts and disturbs and corrupts basically what you're seeing. But from out in space, you do not have to worry about the atmosphere because you're outside of it. And from out in space, so that you get no atmospheric seeing. You don't get that interference, and also you can see all parts of the EM spectrum. Remember, from Earth we can't see X-rays, we can't see most of the UV rays, we can't see parts of the infrared and infrared spectrum. Now Hubble, I do know that Hubble has got equipment on it for recording visible UV and what else? Infrared, I believe. Yes, infrared radiation. All of those equipments is on board. There'll be other telescopes that we've got out in space that look at other parts of the spectrum, but these are parts that, are used by the Hubble Space Telescope. Okay, so there's some obvious advantages of using a space-based telescope. So this begs the question, why don't we do all of our telescopes in space? Why even bother doing them on the ground at all? So let me just put this here. Have a go. See if you can tell me why then, if we've got all these advantages here and the potential problems with using on the ground, why do we bother? Why bother? Well, space-based telescopes are not without their problems. Some of the problems with space-based telescopes are that they are very expensive comparatively. Not only do you have to launch them into space, you've got to design really complicated equipment, and then you have to control it all. It's controlled remotely by remote control from Earth. Now this means that humans aren't here. There's no people on Hubble. It's being controlled by computer from the ground. And if it's controlled remotely, if there's a problem, with your spelling, if there's a problem with the telescope, we can't immediately fix it. Problems with a space-based telescope are big problems because they're so far away and so inaccessible. If you wanted to bring this back in to do repair work on it, you'd have to hook it up to an international space station or even land it again, which would be really, really difficult, time-consuming, and very, very impractical. So problems are big, 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 big problems. Big, expensive problems. And so say I launch this, I spend millions of dollars getting it into the sky, and within a month, one small component breaks down. Say, I don't know, there's a problem in the circuit and it loses power, then it's out of commission. And it might take me months to get back to work. So any problem is costly and causes a huge time delay. So you can get very, very far behind with your project. So it would be great if we could put all of our telescopes into space, but it costs way too much and they're actually quite hard to manage. Our ones on the Earth, we can go in, we can tinker with them, we can work on them, they're accessible, and there's sort of like a trade-off between cost and user-friendliness or ergonomics. Yeah, the ergonomics, how user-friendly is it? Space-based telescopes are not very user-friendly because the users are all on Earth and the telescope's way up in space. And one final advantage of doing it on, or one final problem with doing this in space, is that we cannot physically send up a 20-meter long, a 20-meter diameter mirror into space. So it's difficult to get a very large aperture telescope into space. So if you want something with the largest aperture possible, it's actually more practical to set that up on Earth, and to launch that into space would just be insane and impossible, completely impractical and unachievable.
Now it's time for our wrap-up. Let's give it everything we've got. Ready? Begin.
So, let's wrap this up. What I would like you to do is to try and see if you can do a wrap-up. We're talking about choosing a telescope location, Earth or space. So, you have a go at this, please. For Earth-based telescopes and space-based telescopes, can you jot down for yourself some advantages and disadvantages, and then I'll do so quickly as a wrap-up.
Answer me.
Okay, so from Earth, we can access them easily, and they're much cheaper than doing it in space. I'll put down that's a problem with space, very expensive and bad for access. Space, we've got no atmosphere in the way, which means we've got no refraction, no twinkling. We've got all parts of the EM spectrum visible. And well, some of these are all good things about space. These are all problems here. So other problems, pollution. This could be both light pollution or actual atmospheric pollution. Weather conditions on Earth. You get a bad night's weather, you can't do any astronomy for a while. Okay, from access here, so for repairs, you can make changes to it. So if you want to redesign your telescope, you can do so. And one more small point is that on Earth you can use a much larger mirror than is achievable in space, because you physically can't send up a huge mirror into space, which can be a limiting factor. And as far as I can think of, that should just about do it for there. This is considerations for when we choose where to put our telescope. So we've now spent a whole few lessons and a whole few videos looking at what telescopes are, how they work, and some of the practical concerns. Why don't we do some looking into space? And the whole next section of videos are going to be about what we see when we look up into the heavens.